So thanks to the organisers for giving me this opportunity. Just realised I'm not actually going to give you any time-symmetric ontologies for quantum theory, so I hope nobody's too disappointed. What I'm going to do is talk about some stuff I've been thinking about with the previous map, which is kind of in response to this argument that Hugh presented on the first day with these beam splitters and stuff that was supposed to go from an assumption of time symmetry to a conclusion of retrocausality. And what I want to do is really three things. First of all, I just want to kind of play around with the question a bit, kind of reformulate it in sort of a way that a simple-minded quantum information person like me can understand. And kind of in the process of doing that, sweep a load of important stuff under the carpet so that I can just kind of focus on the narrow issue that I want to discuss. And the narrow issue that I want to discuss is that there's an assumption going into the argument to do with the interpretation of the quantum state that kind of set alarm bells ringing as soon as I saw it was being made. And the other mat had a similar response to that. But we felt like maybe this assumption wasn't actually necessary to get the argument to work, and that turns out to be the case. So the third thing I want to do is to show you how that goes. Okay. So the first thing that is going to be a bit weird in this reformulation is that I'm not really going to say very much about retrocausality. And that's because I want to formulate this whole discussion within the standard ontological models framework that people generally use for no-go theorems. So I'm going to completely ignore everything that Matt said in the last talk and just use the kind of standard ontological models framework like that your grandmother used. And that framework just has an assumption of no retrocausality just like built right into the basic framework. And so I'm just going to just use this basic framework. I'm going to add an assumption of time symmetry, and then we're going to see if that fits in with quantum theory. And if it doesn't, then the conclusion is going to be, well, either you drop this time symmetry assumption, or you drop the standard ontological models framework. One way you could drop the standard ontological models framework is to add retrocausality, and there's a sense in which the proof kind of seems to be pushing you in that direction, but there are other options open to you. For example, rejecting the assumption that measurements have a definite outcome, anything like that. So if you're worried, where's retrocausality coming into it? It's just hidden inside the word ontological model. Okay. But I am going to talk about time symmetry, and if I'm going to talk about time-symmetric ontologies for quantum theory, the first thing I need to worry about is, well, does that even make sense? Is quantum theory time-symmetric? So if you just kind of look at the standard sort of operational quantum theory, it doesn't really look like it. So a random preparation is described by a collection of positive operators that sum to a trace one positive operator. If you're not quite used to seeing things in this way, the probability of each preparation is just in the trace of row A, and then this sum on the right is the average density operator, which has to be normalized. Whereas a measurement is associated with a PAVM, which is, again, a collection of positive operators, but this time it sums to the identity operator. And then you combine these guys to get probabilities. I'm not going to talk about transformations really in this talk, so you just combine your random preparation with your measurement, and using the Born rule, that gives you the probability of that particular preparation occurring and getting that particular measurement outcome. And, at least that kind of looks symmetrical. It doesn't matter which way around you put rho and E in that equation. But so we've got this problem that if we just kind of naively thought, well, a measurement is something like the time reverse of a preparation is something like the time reverse of a measurement, the formalism isn't reflecting that. An ensemble and a PAVM really are quite different things. So that the first thing to notice is that a PAVM is not a valid ensemble, but that's just kind of to do with the sort of normalization convention that's normally used. So if I just define trace with a squiggle on it, okay, at least in finite dimensional quantum theory, it's just a normalization thing. So I'm working in finite dimensional quantum theory, I'm considering a d-dimensional Hilbert space, and I'm just going to define trace with a squiggle on it to be 1 over d times the usual trace. And now, again, I just define ensemble and PAVM and the probability rule in exactly the same way. I just put squiggles on the trace. But now, with this new definition of trace, the trace of the identity operator is 1. Okay? So instead of the maximally mixed state being identity on D, it's just going to be written as identity. And the 1 over D is just going to be put back in through this redefinition of the trace. So I haven't really done anything except that now we can at least say that a PAVM is a valid ensemble. Okay? So if we turn our picture upside down, what was a valid measurement is now going to be a valid preparation. But we've still got this problem that what was a valid preparation might not be a valid measurement, because just because it sums to some trace 1 operator doesn't mean it sums to the identity. And this I don't think is just a normalization convention or anything like that. This is really reflecting an operational asymmetry, which is that we know how to send messages to the future, we don't know how to send messages to the past. Okay, so I can choose between 2 different preparations at the start of the experiment, and then using some measurement at the end of the experiment, I can read out a message. But I can't choose between 2 different measurements at the end of the experiment to send a message to somebody at the start of the experiment. But, does this mean that quantum theory has discovered some new deep asymmetry in the fundamental laws of physics? I would say that's probably pretty unlikely. This is probably just, exactly the same asymmetry that means that I can throw something at you, but I don't know how to just make something come straight towards me, other than saying something very controversial or something. So this is probably something to do with the usual thermodynamic hour of time, and so we just need to somehow try and disentangle that from quantum theory and hopefully be left with something that's time-symmetric. So just to help about thinking about how to do that, it's useful to kind of combine both of these notions of a random preparation and a measurement into one notion, which is a quantum instrument, which is just a collection of completely positive maps that sum to a trace-preserving map. And an ensemble is the special case when the input Hilbert space is trivial. PAVM is the special case when the output space is trivial. And now we can kind of see that this asymmetry really just comes in this condition of trace preserving here. If you kind of turn the picture upside down, the equivalent condition would be that the sum of these guys is unital, which means that it maps the identity to the identity. So that kind of gives you, when you look at it that way, there's sort of 2 obvious options to proceed if you want a time-symmetric formalism. The first would be to drop the trace preservation requirement. So now an ensemble is a collection of positive operators, POVM is a collection of positive operators. But now I probably still want the probabilities to sum to 1, so I'm just going to normalize them by hand. And if you go down this kind of road, you have to kind of worry about, what this formula really means. How can you really implement these kind of things? But that's something that lots of people have discussed. And that's fine as far as it goes. But if I don't just want to talk about quantum theory, I want to talk about these ontological models. And so, if I've got headaches just understanding what this means at the operational level, if I'm then trying to build an ontological model for it, I'm going to have twice as many headaches. So for our purposes, we can just kind of take the cheap way out, which is to keep trace preservation. So we don't need to worry about normalization. We don't have to worry about whether we need post-selection to implement these things or anything like that. And so now an ensemble is going to be a collection of positive operators that sum to the identity. Remember, the identity is now the maximally mixed state because of this new normalization convention. And a POVM is still, just like in normal quantum theory, a collection of positive operators that sum to the identity. And now the rule for the probabilities is just the usual one. Again, it's symmetric between preparations and measurements. And so, apart from that I've used different letters, there's really no difference here in the definition of an ensemble and a POVM. And this is a strict subset of the usual everyday quantum theory with no post-selection. So we know we can do all of this. We know there's other stuff we can do, but we know we can do all of this. And this looks time-symmetric. So this is kind of a natural target to ask for a time-symmetric ontological model for.
So quickly, so option 1 is like post-selection, and option 2 is like Hughes even the left, taking away your ability to.
Right. Yeah. Okay. Sorry, I should say that this whole game you can view as just some way of implementing this idea that there's this daemon on the left or whatever. There's some restriction that prevents you from using the normal ability in quantum theory to send messages forward in time. Okay, so with these restrictions, you can neither send a message forward in time nor backwards in time. So if this all looks a bit artificial and you think the daemon on the left is a much better way of thinking about things, then just stick to that, because what I'm about to say doesn't really hinge essentially on this. It's just kind of helps me understand what's going on. Yeah?
So, is this just one global time and sending things forwards and then backwards in time? And you could do that, a lot. I mean, what about a sequence of measurements? I mean, you're never going to get something which is symmetric under permutations of your POVMs, of your instruments. I mean, there's always going to be some order in linear order.
I guess I'm only really worried about running. I'm just thinking of time symmetry as being like if you run a video forwards,
the whole thing.
Run the whole video forwards or the whole video backwards, you shouldn't be able to tell which is the backwards video.
It's sort of a bit misleading to start sending messages backwards and forwards between one thing and another thing. Sorry. Maybe you can talk after.
Okay. Was there another question?
Oh, well, yes. So it appears for me that if you really want to talk about time symmetry, a better place to start would be to talk about already two-time states and Krauss operators rather than POVM elements, which the POVM element doesn't care what you prepare with a state measured measure. cross operator tells you both about the past and the future. So that seems to me a much better start.
Yes, but I kind of still want to. So there's kind of a difficulty. That's one of the things I was trying to sweep under the carpet here, is that time symmetry is really supposed to be something about, like, you've got a video of the entire universe and you play it backwards. What happens with that? But I don't want to talk about the entire universe.
Just a small laboratory, small system, isolated system.
Right. So I just want to talk about a single experiment or something like that. And so I need to be able to just have nothing coming in at the start and just do some preparation. And then I want to just be able to do a measurement at the end with nothing coming out. I mean, certainly, one thing I could do is just say the only thing I'm allowed to do is unitaries. But then it's not clear how you would set up this kind of closed experiment that I want to talk about.
You did talk about Krauss operators on the previous slide.
No, those were POVM elements.
Yeah, so I could have, in between the preparation and the measurement, I could now allow a collection of positive operators summing to a trace-preserving unital map. But
No, those are POVM elements. Those are not Krauss operators.
no, a quantum instrument is described by Krauss operators.
But they are not positive.
I'm talking. they form a completely positive map on the density operators. I don't think we're okay. Okay, so I'm just going to consider this. So I've already thrown out transformations, and now I'm throwing out most of the preparations, and I'm just really considering this tiny bit of quantum theory where you're preparing some decomposition of the maximally mixed state, and then you're doing some measurement. There's no obvious time asymmetry there, and I'm asking whether what's really going on in such an experiment can also be time-symmetric. Okay, so what do I mean by what's really going on? That's where this idea of an ontological model comes in. Apologies for my artistic skills. So this is the preparation device here. This is the thing that's described by this ensemble in quantum theory. This is the measurement device. These are lights that flash showing you whether A is -1 or +1. And then we notice that which lights flash here is correlated with which lights flash here. And we kind of naively think, well, there's something going from this box to this box. Maybe that's what explains this correlation. And so we just kind of do the most simple thing, which is just to suppose that there's some description of what's going on between those two boxes. Use this letter lambda for that. And then we can come up with some probability distribution for that whole thing, and we can require that it factorizes in this way. Okay, so this just means that we imagine that our A is randomly generated here, it's this bit, and then based on that, some this guy is normally called the ontic state. Some ontic state is chosen based on that A. That goes over here to the measurement device, and now the measurement device decides which outcome to give, possibly probabilistically, based on this ontic state. Okay. Actually, at this point, there's not really much to say about time symmetry. Okay, this is all I'm saying here is that A and B are conditionally independent given lambda, which doesn't really treat A and B differently. This kind of isn't the interesting thing. The interesting thing to think about in ontological models is what happens when I consider different preparation boxes and different measurement boxes. So now imagine that we've got some collection of preparations, some collection of measurements, and now if we've joined up a particular preparation X with a particular measurement Y, then our ontological model should tell us what's going on in that situation. And if I just slap those labels onto everything, I'd end up with something like this. But that's not what we do in a normal ontological model. The first thing we do is notice that the probabilities over here don't depend on which box we've put over here. That's just the normal operational no signaling backwards in time. So we can get rid of that. Then suppose that there was signaling forward in time. Suppose that which light flashed here depends on which box we put here. Then the natural thing to do would be to say, well, the correlation between x here and the flashing over here, that should also be explained by this lambda. And so the outcome over here should only depend on x through lambda and not have this direct dependence. And then the last thing we do, which is really the place where sort of a no retrocausality assumption enters most explicitly, is that we say that the probability for this lambda should only depend on what's going on in this box, the label x and the outcome a. We're kind of imagining that it might come out of here before we've even decided what box to put over here, and so we can't allow this dependence here. Okay? And now this is just the standard definition of an ontological model for this setup. Okay? Which light flashes over here depends on which box we've got. Which lambda comes out depends on which light flashed and which box we've got. And then it goes into this box, and it gives some outcome based on the lambda and based on which box it is. Okay? So this is the standard sort of assumption that's lying behind the kind of standard no-go theorems. Okay? And now I want to talk about time symmetry, and there's all sorts of ways in which you could try and impose this, but we can actually get away with pretty much the most minimal thing you can imagine, which is just requiring that if you kind of imagine, this is what you'd see if you watched the video. Okay, you'd see that there's these particular boxes. Maybe you have to watch millions of videos, and you see that some proportion of the time these particular lights flash and a particular lambda goes between them. And if this is a valid ontological model, then it has to be written like this. But if when we play the video backwards, we don't want to know that, we don't want to be able to tell that it's being played backwards, then a minimal requirement would be that what we see in the video still makes sense as an ontological model when we play the video backwards. And so that means that this thing should be, as well as writing it in this normal ontological models way, we should be able to write it in the exact opposite way and imagine that what was the measurement is now the preparation, some lambda comes out of that, and then what was the preparation is now the measurement, and the outcome of the measurement is produced in the normal way.
Isn't this somehow stronger than what we normally call time symmetry? It's something like a statement that the actual state of the world is time symmetric. Not that a process which can run one way can run the other way. Which is the weaker.
I'm only trying to do the latter one. So I'm saying you've got your experiment like this. You explain it using this ontological model. And now we want that if we played the video backwards, what we see is something that would be allowed. Okay? Doesn't have to be the same as what it is when the video goes forwards. Just that it's something that
the same probabilities. In other words, it's somehow you couldn't tell which way the video was being played. But like if we were doing classical physics, we could play, a slice of light backward. It would look completely crazy, but it would still satisfy the equations of motion.
Right.
Aren't you excluding something like that? It's like a condition on the initial state as well, or something that it'd be time symmetric, be compatible with time symmetry.
For instance, this would exclude a thermodynamic asymmetry just as well as a fundamental asymmetry.
I don't think so. So I don't mind if when you play the video backwards, the video looks extremely implausible. All I'm demanding here is that you can make sense of it as a valid ontological model with that direction of time.
Why should it be the same lambda? We don't observe the lambda, no?
Well, I'm imagining you do, okay? So if all you observed was the operational thing, then running the video backwards, all we could demand was this operational time symmetry that I was talking about in the first part of the talk. But now I'm trying to impose time symmetry on the ontological model, which means I've got to imagine this video has got the lambda in it. And now I'm demanding that when I watch that video backwards, it still makes sense. How much time have I got? Okay, go on.
So you say that you don't mind whether it's really looks very implausible if you play it backwards. That would seem to suggest that when you play it backwards, you should be able to have a much lower probability of that situation happening than when you played it forwards. Yet here you're demanding the same probability for AB lambda, whether you explain it in a forwards direction or a backwards direction. Whereas if you have your glass smashing and reforming, I would want that to have a much lower probability if I'm running it in the backwards direction as opposed to the forwards direction where I drop it.
When it has probability 1 in the backwards direction, you'll see it in the state. It's deterministic.
I'm a little bit concerned that we're operating here under the constraints of a feature boundary condition called lunch. So I'm very concerned, out of fairness to Matt, that he not be interrupted too much so that he can finish at least some reasonable proportion of his talk. So I'd like to propose now that we go back to a standard talk format and keep the questions to the end if possible. Thanks.
How much time have I got?
You've had 25 minutes so far, so there's another 35 minutes left for the whole thing.
There should be plenty of time for questions, so don't worry. Okay. So yeah, I mean, there are lots of interesting questions about what time symmetry means in a world that has probabilities built into it. And I guess at this point I'll just say that's another thing I'm trying to sweep under the carpet. And this seems like just the most naive way to say that the video running forwards makes sense backwards as well. Okay. So now we've set up this definition. The obvious question is, does this universal part of quantum theory, this one where the only preparations we can do are decomposition of the maximally mixed state, admit a time-symmetric ontological model or not? And this seems like the sort of question that this time-symmetric argument for retro-causality or something was supposed to be addressing, okay? So you can find it here, and I learnt it from this nice paper here. So the argument basically goes, you've got these two polarizing beam splitters, you've got the daemon over here controlling which path the photon comes in, comes out here, and then comes out this polarizing beam splitter. And the argument is pretty simple, really. It's that the polarization of the photon that comes out here is either equal to the angle sigma L or equal to the angle sigma L plus 90 degrees, depending on which path it came in here. And this angle here can be completely arbitrary. Okay? So when we play the video forwards, we see photon comes in one of these paths, comes out here with some polarization, either sigma L or sigma L plus 90, and it goes through here. And if we played that video backwards, we'd see photon coming in one of these paths through this thing that's angled sigma R, and yet its polarization would be either sigma L or sigma L plus 90, which is not something that we would have allowed in the forward time direction. Okay, so it looks like we've got a situation here. It's time symmetric at the operational level, and yet our description of what's really going on doesn't respect that time symmetry. And the thing that me and Matt didn't like about this argument is what's called the realism assumption. Okay, there's kind of at least 3 different things that people mean by realism in quantum foundations. The weakest is just kind of scientific realism as a general attitude. A slightly stronger thing is the kind of jargon used in discussions of Bell's theorem and things like that, where realism has something to do with believing the existence of these lambdas. And then the strongest thing is realism about the quantum state itself. Okay? The idea that when we assign a system some quantum state psi, we're really imagining that that system itself has the property of having the quantum state psi. And the realism assumption that's entering here, remember we're talking about single photons here, so polarization is just a feature of the quantum state. And so the assumption that's entering here is that we're being realistic about the quantum state. We're assuming that the thing that comes out of here is actually described directly by its quantum state. And there are already plenty of reasons for thinking that reality isn't described directly by the quantum state. And so for people who buy those sorts of reasons, the obvious escape route from this argument is just to reject this assumption that what really comes out of here is the quantum state. And I'd like to just give an explicit example of how that might work. So let me first just try and reduce the argument to the kind of minimal possible example. So I'm going to call horizontal polarization 0 and vertical polarization 1. And I'm just going to define these guys, which are diagonal polarizations. And now I'm just going to imagine that we have 2 different choices of how we set up a polarizing beam splitter. We either set it horizontally, and then, if you like, the daemon decides whether we end up with horizontal or vertical, or we set it diagonally, and the daemon decides whether we get plus or minus. Okay? In the normalization convention I'm using, when I write these like this, they each have probability of half. And then we're going to use exactly the same measurements. We're either going to measure horizontal versus vertical polarization, or diagonal versus anti-diagonal. Okay? And the quantum probabilities for this case are pretty simple. If the ensemble matches the measurement, then you get perfectly correlated outcomes. So if you prepare 0, you'll measure 0. If you prepare 1, you'll measure 1. And each of those happens with probability half. And if they don't match, if you prepared this and measured this, or vice versa, then everything's just completely random. Okay? There's a 1/2 chance of preparing each of these, and then regardless of which one you prepared, there's a 1/2 chance of getting each outcome. This is a pretty small subset of the original things that were being discussed where we considered any angles, but it's still enough to run this argument. Okay? If we imagine playing a video forwards where we prepare like this and then measure like this, then what comes out of the preparation device is, if you assume that the quantum state is real, is either 0 or 1. Okay? And then it goes into this measuring device. But if we prepared this, which is what we'd be doing if we played the video backwards, then we would expect that what comes out should be either plus or minus. Okay? So just with these minimal things, we can still run the argument. But now, if we just weaken this realism assumption from being realism about the quantum state to just this demand for the existence of an ontological model, then there is a time-symmetric ontological model for these quantum predictions. It's pretty simple. just consists of 2 classical bits. When you do a preparation, if I do the first preparation, then the first bit just gets set to whichever outcome of the preparation. The second bit's random. If I do the second preparation, second bit gets set to the outcome, and the first bit's random. And when I do the measurements, if I do the first measurement, it just reads out the first bit. If I do the second measurement, it just reads out the second bit. A pretty simple model. So if you just watch a video of this model, you see the preparation, you see a bit coming out, you see these 2 bits coming out, and let's say you did the interesting case where you did, say, this preparation and this measurement, well then the first bit would be encoding whether you got the 0 or the 1, and the second bit would be encoding whether you got the plus outcome or the minus outcome. There's no retrocausality here. That second bit was chosen randomly during the preparation, and then it's just being read out at the measurement. Okay? But the way I've described it, you could just as well interpret that in the reverse direction. The second bit was chosen based on whether the preparation was plus or minus. The first bit was chosen randomly, and that was what determined the outcome of this measurement. Okay? So this is just all to show that without this assumption that the quantum state is real, the argument doesn't go through. Just to make that a bit more explicit, if we draw the 4 possible ontic states like this is the first bit, this is the second bit, then when we prepare either 0 or plus, we're preparing either 50-50 of these 2 states, 50-50 of these 2 states. When we prepare plus or minus, we're doing it like this. And what allows us to escape the argument is that the same ontic state appears when you prepare 2 different quantum states. Okay? So it really is down to the meaning of the quantum state in the model. And in fact, this model is exactly Spacken's toy model, okay, which reproduces the quantum predictions in this very simple case. And if you look at some of the other toy theories, there's one for odd-dimensional stabilizer formalism and one for Gaussian quantum mechanics, then I think if you restrict to the unital parts of those theories, you should get a completely time-symmetric, non-retrocausal, sensible model for some interesting part of quantum theory. So if we're going to have an argument that rules out these time-symmetric models, we're going to need to be a bit more careful about exactly which quantum predictions we use. So let me just restate the conclusion of the existing argument in my language. Unital quantum theory is incompatible with psiontic, meaning models where the quantum state is real, time-symmetric ontological models. Okay? And you can compare that to something that, calling here EPR's lemma, it's just like something they happen to mention. They're trying to argue that the quantum state is an incomplete description of reality, but along the way, they essentially prove that under an assumption of locality, it's possible to assign 2 different wave functions to the same reality. So when me and Matt saw this, we thought, well, this is really interesting because they've managed to get as far as the kind of EPR version of the argument. I think a few talks so far have tried to get Einstein on their side, so I'm going to do that here. I'm going to say that if Einstein saw this argument, rather than jumping to retrocausality, I suspect that he would have disagreed with this assumption here. And if you look at this paper, you'll see formal definitions of things like psiontic and a nice discussion of what Einstein's views on this distinction were. Okay. So now I'm going to present a version of the argument that doesn't have this assumption about the status of the quantum state in. And it actually turns out not to be too difficult. The reason is this is my definition of what a time-symmetric ontological model has to satisfy. And now let me just sum over A and B on both sides of this equation. Okay? So this just goes away very quickly, and then we're left with the sum over the remaining variable with these terms. So that's this equation. And in particular, nothing over here depends on x, which means that from the assumption of time symmetry, we find that for any box x, the average distribution over the lambdas, when we average over all outcomes of the preparation, is independent of the box x we've chosen. And to connoisseurs of ontological models, this might look like a familiar assumption. For completely independent reasons, it's been proposed that an ontological model should have the feature that if, at the operational level, when we average over some random preparation, say we have two different random preparations and they average to the same average density operator, well then that means that no matter what measurement we choose, there's no way of distinguishing between those two preparations. And the natural explanation for that in an ontological model would be that this distinction without a difference is no difference at all. Okay? That in the ontological model, when we average in exactly the same way, when we average over the specific outcomes of the preparation, the distributions over lambdas we get is independent of x. Okay? So the implication in this way, in this direction, is kind of automatic. Okay? If the distributions over lambda don't depend on x on average, then it had better be that they average to the same density operator, because otherwise our model's not going to be able to reproduce that difference. And the assumption of preparation non-contextuality is that the most natural explanation of this independence at the operational level is this corresponding independence in the ontological model. And this assumption was first defined by Speckens. Okay, so if I just go back, I've got this equation here as a consequence of the assumption of time symmetry. I find that the distribution over lambda averaged over A is independent of x. And then under the assumption of preparation non-contextuality, I also have that the distribution over lambda when you average over A is independent of x. And indeed, because I'm restricting to this case where everything is just a decomposition of the maximally mixed state, this first assumption is just satisfied automatically. Okay, this is always just the maximally mixed state. Which means that for universal quantum theory to have a time-symmetric model, it has to have a model that satisfies this. Which means, in particular, in the case where we consider different decompositions of the maximally mixed state, it's going to have to satisfy this, which means it's going to have to be a preparation non-contextual model. But as soon as this definition was proposed in the very same paper, it was proven that preparation non-contextual models for quantum theory don't exist. And luckily for us, essentially all the proofs that have been given fit within this universal quantum theory. Okay, so they're all about establishing the preparation contextuality of the maximally mixed state. And so, I mean, we're done, basically. Someone else has already done the hard work for us. As soon as we notice that time symmetry implies this instance of preparation non-contextuality, we just say, well, since someone else has already shown that that assumption of preparation and contextuality is incompatible with quantum theory, it must be that time-symmetric ontological models are incompatible with quantum theory too. So I don't want to go through a whole proof of preparation and contextuality because, it's not really relevant to the discussion. But just to give you an idea of how they go, there's a particularly nice proof in this paper where they just consider decomposing the maximally mixed state into these two decompositions on the Bloch sphere. And then they do these two measurements. It's very reminiscent of what gets you a maximum violation of the CHSH inequality. But this is all just on a single qubit. And they basically, if you consider this preparation to be encoding 2 bits, they argue that the assumption of preparation and contextuality essentially only allows the ontic state to encode one of those bits. And yet, these quantum measurements allow you to read out a bit of your choice with 85% success probability. And so there's no preparation and contextual model for this situation, and hence there's no time-symmetric model for this situation either. So the conclusion is now pretty much like this conclusion before, except without this word scientic. Okay? This part of quantum theory that looks time-symmetric operationally is incompatible with time-symmetric ontological models. It doesn't satisfy them. And so with a conclusion like that, it's really up to you what you take from it. You could say, I don't believe in quantum theory. It's pretty unlikely. You could say, I don't believe in time symmetry. Or you could say, I don't believe in your ontological models. Okay? And one way of doing that would be to say, I don't like this assumption of no retrocausality that enters into the ontological model. And indeed, this proof is kind of pushing you in that direction, because our problem was that we found that, on average, the ontic state wasn't allowed to depend on which preparation we'd done. And that basically comes from the time reverse of the requirement that the ontic state can't depend on which measurement you've done. Okay? So you could say that it's precisely, in some sense, the assumption of no retrocausality that has led to this, with the help of time symmetry, has led to this assumption of preparation and contextuality that's created the problem. Yeah, I guess I'll leave it there.